Hello everybody, welcome back to another glorious maths video. In this video we're going to be looking at the dual notion of projective modules, so that is injective modules. And these are going to be useful, they're a useful type of module which we're going to be looking at later on in the series, and so I feel that introducing them is necessary. And so I'm just going to define them, and then again they're dual notions, so they also have a relation this time to the contravariant functor Hom rather than the covariant version we saw in the last video. And there are a few other theorems about, for example, like direct product, and there's a criteria for injective modules. I forget the name of it right now, but it's really important. So, and the proof is really long, so I'm just going to state it to finish off the video. So yeah, hopefully that should be a good amount of information on them. So let's just get straight into it. So again, I said that injective modules are the dual notion of projective modules. And so recall that from the last video that projective modules can be given by a commutative diagram. So for injective modules, what we're going to do is just reverse all of the arrows. So the definition is, we say that, let's just say E is injective if, and then, okay, what are the conditions? For R modules M and N, the following commutes. Alright, so what we're going to have. So the bottom row again is going to be exact, but in this case, instead of us having, sorry, let me just draw this out. Gonna have F going via N. Instead of us having a surjection like we did last time going this way, this time F is an injection. And now we're going to go up this time to E via some G, and there exists some H like this to make this commute. Where, again, this is an R module homomorphism, G is an R module homomorphism, and F is an injection, so that this is exact. Okay, so, again, so, first of all, let's just prove the following theorem. E is injective if we have that Hom of E is exact. Okay, so proof. So again, this is not going to be too difficult. So again, notice that this is a left exact functor, and so what we want to do is show that for any injective module we have that. So for some injection, I don't know, F from M to N, we have that Hom M E is a surjection via the induced map, and this time I meant, this time I meant composed with F. Last time I meant this. Sorry, I pinned it in the comments along with Christian Foucault's notes. Thank you for that, by the way, again. Anyway, I digress. So this time it is, the induced map will look like this, and we have to show that it's an surjection. That's where the proof lies, because if it's a surjection, then the left exactness of the Hom, the contravariant Hom functor, will carry us the rest of the way. And so, well, the surjectivity of this is blinding is by this is just a different way of saying this definition, because, well, for any homomorphism, so for any G, let's just write this down. For any, I'm rambling, so let's just write this down. For any G in a hom here, we have that G composed F equals some H. So we have that there exists a H in the image. We have that there exists a H in hom of NE, again by definition, such that H is in the image of composed F, and therefore it's a surjection. And so the other way around is exactly the same. So if this is true, then this is true. So it's really just another way of saying the theorem. It's not difficult to prove at all. Okay, so now that we have that out of the way, we can proceed to prove the following. So let me just state the theorem. What does the theorem say? Well, the theorem says that if we have a family EK of injective modules, then E equal to the direct product over all of these K of EK is also injective. And I'm going to make use of some commutative diagrams, so I'm just going to give myself the next board. So, proof. Okay, so what the proof of this is, okay, so because we know that each, so, okay, let's see, we'll write, okay, so let's just draw out the diagram that we want. So what we want is, we want something that looks like so we want something that looks like this, right? And so the way that we're going to do this is, well, because each of these EK are injective, what we're going to have is the following. We're actually going to have each projection PK going to EK. And so by the... Actually, I'm just going to rub this out because we know what it is. So, okay, there we go. And then by the... And then let's just go a little bit further, like this. And then we're going to have this. Alright, so now by the the injectivity of EK, we're going to have that there exists some HK, such that, so we're going to have G here, and we're going to have F here, let's say. Alright, such that, okay, so we have that HKG is equal to PKF. This should be correct. Let me just check. Yeah, okay, that's right. And now, so that's by the projectivity of this, of each EK. So now, what we're going to do is going to define H from N to E by mapping some, I don't know, some B maps to HK of B. Alright? And so now this does in fact extend F, as one can check. Alright, and so the last thing I'm going to prove is the following. So again, it's quite an interesting link between injective modules and so forth, and exact sequences and such. And what it is okay, so the following theorem is if, so for example, E is injective, then 0, which goes to E, and this goes via some F to A, and then this goes via some via some G to B, and then this goes via some to 0. So if E is injective, then this splits. Alright, and so, now, by the fact that E is, okay, so I'm going to prove it over here, so proof. So, alright, so let's see, because E is injective, E is injective. Alright, so now, because E is injective, this means that we can actually extend, okay, sorry. So, because E is injective, we have the following. We have the E, and then we have an injection going to A. And then we have some map, let's say, I don't know. No, we can't use F. We'll have some map, I don't know, H, such that again, H composed with F is equal to the identity. Alright? And this is just by the injectivity of E, and therefore that's just the proof. It's just a special case. Alright, so now the final thing I'm going to do is I'm going to state, I think it was Brouwer's condition for injectivity, and it's quite a useful theorem. So not proof, theorem. Okay, so what is it? E is injective if and only if every R map where E is an R module, F from I to E can be extended to R, where I is a left ideal of R. Okay, so thank you for watching this video. Hopefully it was informative and hopefully you enjoyed it. And yeah, I'll see you in the next video. Goodbye!